Boston University of United States, a very well-known world-class expert in the field of quantum science and technology. He has kindly accepted our invitation to join us for this seminar, and he's going to talk all about new linear optical approach to quantum information processing and quantum simulation. At the end of the talk, we will have a question-answer session where the questions can be asked by sending a message through the chat button of the Zoom platform. Alexander Sergienko pioneered the experimental development of practical quantum measurement techniques using entangled photon states. He's also especially well known for his contribution to the quantum information processing, including quantum cryptography and communications, quantum networking, quantum imaging, as well as the development of novel, ultra-precise optical measurement and characterization techniques, quantum metrology, which are based on the use of non-classical states of light. Professor Alexander Sergienko received his Master of Science and PhD degrees in physics from Lomonosov Moscow State University in 1981 and 1987, respectively. In this regard, he's my academic brother. Later on, from 1990 to 1996, he was working at the University of Maryland and at the National Institute of Standards and Technology, NIST, in Gaithersburg, Maryland. At the present time, Professor Sergienko holds joint appointments in the Department of Electrical and Computer Engineering, in the Photonics Center, and in the Department of Physics at Boston University. He has published more than 400 research and conference papers and holds 6 patents in the field of experimental quantum optics and entanglement manipulation. He's the editor of the book Quantum Communication and Cryptography and co-author of the book Quantum Metrology, Imaging, and Communication. He's a fellow of the Optical Society of America, a member of APS, the American Physical Society, and IEEE, the Institute of Electrical and Electronics Engineers. With all this, I want to thank Alexander Sergienko once again for joining us and hand over the word to him to begin his talk. Alexander, please, you're welcome.
Okay, just a second, let me share. Can you see, okay, so I need to go. Okay, can you see my screen
it's
well?
Okay now, it's okay.
Okay, good. Okay, okay. Well, thank you very much for the invitation and for the nice introduction. I do appreciate it very much. It's my real pleasure to be here and to talk to such a nice audience, even though I would really prefer to do this in person. And hopefully the future will give us some opportunities to communicate directly and discuss all the issues interactively rather than online. I'm still kind of more, I prefer the real life interactions myself. Anyway, today I would like to talk about the new ways of performing quantum information processing using new linear optical systems. And the outline would be, well, I will start with small introduction, basically. Why do we need quantum simulation of complex physical systems? Then I'll talk about the what is known, what we already have in the field of conventional linear optical circuits for quantum information processing. We'll talk about their good features and some limitations. And I will introduce something that we recently developed, the technology that could bring a new development in this field and not only make things faster, but also open the greater amount of possibilities when it comes to quantum information processing or evaluation of parameters of quantum system Hamiltonians. I'll give a couple of examples. I'll show you some interesting new developments that we still have not found a good application of. If someone would come up after this, have some ideas, I'll be happy to discuss that. Then we'll discuss some quantum entangled gates and some topological effects, because when the elements that we developed, when you put them in, like in the chain or in the two-dimensional plane, they could form some topological features. And the role of topology is very important in the modern quantum information processing. And I will talk about this a little bit, and I'll conclude with some interesting perspectives and just recent applications, some curious, cute ones, and you'll see what it is. Well, why do we need quantum simulation? Well, in fact, we all know that quantum computing is the very popular area these days, and lots of people doing quantum computing. But originally, quantum computing is really was triggered by Shor's algorithm. The Shor developed the algorithm for breaking codes, and to do that, you need to have a quantum computer which executes sequence of gates doing Fourier decomposition and can factor large numbers. And people start building these computers and discover that it's a little bit too difficult to do. And later, over the last like 10, 15 years, the more and more people start looking into the different class of problems, not security, but more like physics oriented. And this class of problems, that was more like going back to the origin of quantum computing, because original work by Feynman back in '82, that's what he suggested. He said that if you would like to evaluate the properties of quantum system, you better do it using some other quantum system. Of course, as always, traditionally, you can do classical computing approach. So you can take a quantum system, you can write a number of equations, depending on how many degrees of freedom the system has. You can write so many equations. It will be a huge system of differential equations, and you can run it through the supercomputer and try to solve it. And we all know it usually takes significantly long amount of time. But Feynman said that if by any chance you can design a quantum system that has the same degrees of freedom as the system under consideration, then even though this quantum system is of different nature, then you can run it and you can read out the result. You don't need to calculate, you just read out the result, and that would be the answer to the question, what kind of energy levels or what kind of Hamiltonian this particular quantum system has. So that was the original approach, and many, well, today it's about 90% of all quantum computing efforts in the world is really about this simulation, Hamiltonian, evaluation of Hamiltonians of the system. And as you know, there are several approaches. There is the cold atoms and cold ions. There is superconducting qubits. There are spins of electrons in solids, and there is photonics. There are basically four major platforms that people using to encode qubits and use those qubits for quantum processing. Well, of course, you know that to work with ions and atoms, you have to cool them down to like 10 millikelvin. You have to do laser cooling, trapping, and it's a huge apparatus with very low temperatures. The same is with superconducting qubits. Superconducting qubits encoded in the nanocurrents, and they simulate the operation of spins. but also they have to be kept at a very, very low temperature in the huge dilution refrigerators and everything. And well, you know about this. What about, well, the electrons in solids? They are a good system, but the noise is still a big problem, because when the spin is embedded in the matrix of the solid state, it really feels all the fluctuations from the solid state. And it's even harder to separate the quantum bit from the external influence in such systems. So optics, the photonics. Photonics has a very unique feature. The photons can go around and you can manipulate them without being worried about interaction with the environment, because the energy of the photon is significantly greater than the external KT defined fluctuations, quantum fluctuations, and you can work with them. The problem is photons are not really particles. They are quasi-particles. There is no mass, and it really causes some problem of using them in comparison to electrons, for example. However, the field had lots of different developments, and we all know that originally there were two interesting designs of quantum gates based on photons proposed by Neil Laflamme and Milborn, and later by Pittman, Jacobson, Franson, using polarizations of photons, correlated photons. So, and this field also is under development, but not so much, because the problem with photons, all gates in quantum information processing are based on the control knot operation. So to do the control knot operation, you have to sample the control to find what is the state of the control, and based on this, do something to the target photon or not to do it. So basically, to do the control, you have to sense what the photon, in what state the photon is, but usually it kills the photon. So that's why you really need to do something about that. And usually people kind of have to make a copy of the photon, have two photons and kill one, but the second one is still available for operation. So it creates unnecessary overhead for the processing, and that's why the really like direct gate-based quantum computing with photons was not so efficient going forward. However, doing the Hamiltonian-based investigation using photons was moving much better. It's all based originally on the original paper by Reck and Salinger back in '94, where they had shown that the photons and beam splitters can realize any unitary transformation in quantum mechanics. The question is just how many degrees of freedom you have and how many photons and beam splitters you need to realize that. And there are a number of modern approaches to do that. And this is just two samples. I picked them up randomly. I mean, it's no any special purpose, just to illustrate what is involved when we use photons for quantum information processing. As you can see, the number of beam splitters or number of couplers here on the chip design is growing very quickly when you start to increase the number of degrees of freedom. Like here's the like 5 lines, and you can see already how many elements are required for that. And when you ask yourself the question, why this is happening, the answer is in the structure of the elements that are used for this. So from the early days of quantum optics, the major operating element is the beam splitter. Beam splitter is the very nice symmetric device with 4 ports. However, this symmetric device, when you start using it, becomes directionally biased, which means if you come from the port 1, you can only go out to the port 3 and 4. You cannot go to the port 2. You cannot go back to the port 1. It's directionally biased, only forward. And this is the kind of well-known matrix explaining the behavior of the fields on the beam splitter. And we all know that it leads to such effects as Hongo-Mandel effect or just any other quantum interferometry effects. So what happens is if you want to simulate the behavior of quantum system, usually some quantum system has a Hamiltonian with multiple degrees of freedom. So your photonic system must simulate the same amount of degrees of freedom. And when you start sending photons through, in order to read out the effect of this system, you have to make sure the photons have a possibility to go through all possible directions of the Hamiltonian, or all possible states of the Hamiltonian. So if it's n, it has to be n possibilities in your system. So to execute this, you have to build your photons, a photonic system in such a way that all these paths will be available. But because beam splitter only allows you to go forward, it starts growing like a tree very quickly. You see, like at every stage, it doubles, doubles. At the end, you will have n possibilities, required possibilities, but the amount of real estate that you have to use to execute it is huge, as you can see. It's so many elements you need to introduce just to populate those degrees of freedom with photons that were originally introduced here at the entrance. So the question we asked originally, is it possible to find some other linear optical element or design it? Because like the quantum engineering is basically a new profession these days, becomes a new profession. We learn a lot from quantum mechanics, from quantum optics. We learn the physics of this, physics of quantum entanglement. And as usually, after you learn things, it becomes your tools. You can you can operate those tools because you know them very well. And operating tools means you become an engineer. You start to design, put together new type of devices. And basically that's what we did. We asked ourselves, can we build up an optical design that has like 3 beam splitters, 3 mirrors, and each mirror has a phase shift associated with that, such that we have 3 ports, A, port B, port C, and this photon can come in through each of these ports, but it can also go out from each of these ports. So to some extent, you can explain this as the scattering matrix, A, B, like 1, 2, 3, 3 by 3 matrix, where each element here will be, photon comes from 1, goes to 1, 1 to 2, 1 to 3, and so on. And because the system is fully symmetric, each port can be input and output at the same time. So what is the system? Of course, when photon comes in, it can go around in multiple ways. But you can, and the characteristic distance here is d. Here it's d, and going to the mirrors, it's d over 2 right here. So you can evaluate after each step, basically the photon can go this way or that way. And here it can, for example, go out or can go back and again, stay inside. And you can calculate that after 10 times, 10 interactions with beam splitters, there is 99.8% per 0.998 probability your photon is out. So nothing is left there. The photon will be out of this system. So it means that this system can be treated as a scattering element with the matrix 3 by 3, such that after 10 times d times speed of light, so time between these two interactions is distance divided by speed of light, 10 times the photon is out. And in order to make it work, in order to introduce, to make sure this can be represented as a single matrix, you have to make sure that within this 10 times, of the distance between beam splitters, the field inside this item is coherent. Well, you can think about this. So even if it's a bulk material, what we did basically, and this distance between beam splitters is 30 centimeters. 30 centimeters in the free space, it's 1 nanosecond. So 10 times is 10 nanoseconds. So the coherence time of the photons, if the coherence time of the photon is greater than 10 nanoseconds, then when photon comes in and goes out, you don't have any information where it is inside this system. So you can treat this as the coherent scattering unit with the matrix of 3 by 3 matrix. So basically this conditions is right here depicted. And your detectors that you use to detect photons coming out of this of this system also have to be slower than 10 nanoseconds. So you should not be able to recognize where inside this system your photon is. So it all falls into the category of coherent interaction. It's like in the cavity, in the laser cavity. You know that photon is inside, but you don't know where it is inside. It's coherent inside. So here it's a system of 3 and can be treated as the single scattering matrix. So the interesting thing is that this matrix can be changed by changing the phases in front of the mirrors, this P phase right here, in front of each mirrors. We can have different situations. If, for example, the phase is pi over 6, the matrix looks like this. This is for the amplitudes. You see, it's all components have magnitude 1 divided by square root of 3, of course, for normalization, all ones, and only this one have a phase coefficient. But the magnitude of all elements is exactly the same. It's 1 over square root of 3. If you take the angle to be minus pi over 2, for example, it becomes a different matrix. You see, there are ones on the diagonal and minus 2, minus 2, minus 2 here. This is the very interesting matrix. It's called the Grover matrix. The Grover matrix has a peculiar application because we all know about the Grover search algorithm. Basically, if you have a system of scattering centers and each scattering center operates as the Grover matrix, the information propagates in such system faster than in the classical network. So that's why Grover search works faster than classical search, for example. I mentioned this right now, but we're not going to use it too much, the Grover, at this point. But at the end of the talk, I will show you what interesting applications could be of that. So that was the idea, original idea that we published some time ago. And then we decided to do experiment to show it that it works. So my student, Shuto Ozawa, he did that. And what he was trying to do, he selected the phase shift to be pi over 6 to have a symmetric 3 by 3 matrix. And this is for the amplitudes, of course, and this is for the probabilities, P. So it's 1/3 of symmetric 1, 1, 1, which means you come here through A, you have equal probability to go back through A, through B, through C, and all other combinations are valid too. So this is experimental data showing how you can realize. You see, the majority of results are pretty close to 33% with the experimental error, of course. And the one thing we learned that you cannot make many of this system in the bulk because stability of this system is crucial for its operation. It's, as always, like any cavity kind of design, must be stable in terms of time, vibration, and everything. So it became absolutely clear after we demonstrated 1 unit performance experimentally that you have to go on the chip to do it in the integrated design. So reduce the size, put it on the stable platform of semiconductor chip, and then you can use them. So that's, I also comment on this at the end in the current development and future developments of that. So such type of system could work. It's been proven. Now the next question is what you can do with that. What's interesting thing you can do with that? So how you would evaluate the Hamiltonian of the system when you use this type of devices, linear optical networks, basically. What you can do, you can make a network of such unit. It's a it's a triangular, basically, 3 nodes, and it's very easy to connect them in the network. And then you start sending photons inside there, probing your system, and you will have detectors outside that detect the arrival times. So, and what we know about that any evolution of the quantum system can be described by the unitary operation. This unitary operator is related to the Hamiltonian. At the same time, because like we all know problems of like electron in the crystal lattice of solid state. That would be the closest physical analogy of this. If you keep sending it, so you will have a function described in this wave function is the periodic function that where you can introduce the momentum, quasi-momentum and coordinate. So the same is for photons. If photon is going on the chain of scattering centers, it's called the quantum walk, basically. It goes in, and at every center, it can go in different directions with some probability. That's what the quantum walk is about. But when you know parameters of this system, you can introduce the K vector for this type of propagation of the photons on the photonic lattice. But I just want to point out, this is the photons on the photonic lattice. It immediately builds up a possibility to simulate electrons on the crystal lattice, for example, so for solid states. And that's how you can find the Hamiltonians of this. If you can find this function, then you can recalculate the Hamiltonians as well. What the benefits of using our designs versus existing one? There are 2 benefits. Well, first of all, our matrix is not 2 by 2 as original beam splitter, it's 3 by 3. So it can populate higher dimensional spaces faster. But also the biggest advantage here is fully reversible. It's directionally unbiased. That's a very important feature here in comparison to the beam splitter. Beam splitter is directionally biased. It's only can go forward. And if you want to populate more modes, you have to increase amount of spatial modes. And at the end, you have to have detectors at each of these outputs to detect those photons. And that's how the majority of experiments have been done so far. In our system, well, this one is even more, it's like the branching tree, as you can see. Here it's even more detectors are required to have n elements to be tested. In our system, because photons can go back and forth in the system, the amount of opportunities are spread in time. So you have to have a detector here, and this detector will detect when the photons will arrive, and it will correspond to different probabilities that originally here with the beam splitters were like in parallel. Here it's in sequence. In principle, to have a good quality evaluation of the Hamiltonian, you have to have exactly the same number of outputs as in any test. So if your system is n-dimensional, you have to test all possible probability amplitudes of parameters inside the system. And it's better to test them multiple times because it's all statistical. The quantum walks is a statistical type of investigating or measuring systems, but it fits very well with the statistical nature of quantum mechanics. So instead of like n detectors here, we will need only one detector. And instead of multiple elements here, we will need just one chain of elements. So we reduce the number of elements. The time-wise is about the same, but the number of elements, the real estate required to execute this problem is significantly lower. Significantly means one order of magnitude. If this one requires n squared, this will be n. If there are problems that requires n cubed, we will be n squared. So our reversible, fully unbiased design allows you to save one order of magnitude on real estate of elements if you try to solve the problem using photonic quantum walks and photonic scattering problems in quantum information or in quantum simulation of Hamiltonians. So one other example, I told you, so the quantum walk of photons on the network of such elements could simulate the behavior of electrons in solid states. If you make a very, very simple like ladder type configuration, each triangular here is this unit that we discussed, three edge node, like 1, 2, 3, 1, 2, 3, the same as we had before. Each one can be treated as this scattering matrix that I presented before. Then you can evaluate that if you keep sending photons through, there are multiple opportunities here. There is transitions like here, here, or now the transition between two of the elements and in reverse also. So at the end, you can find there are three different opportunities for different transitions. And when you solve the problem for eigenvalues of energy, it will be three types of energy. And they are dependent on the K vector. It means on the design of your lattice here. So you can simulate this and you can come up with something like this. You can see this is energy. It's just a stable level. The second one, the red one, has, it's on the horizontal axis, there is a K. Here's this energy or quasi-energy. It's equivalent to the Brillouin zone, basically. And you can see that such a simple configuration of quantum walk on the system of these units can immediately start simulating semiconductor. There is a band gap right here, band gap right here between this. So you can start simulating things. You put different structure of this unit, those cells. Here they're square. It's a very, very simple. So you can put hexagonal or anything, and you can go to more complex physical system. So you can start inventive kind of simulating behavior of solid states. So that's an application. And later, just a little bit later, I will show you the other opportunity, what you can do with that. Actually, let me skip this one and go directly to this one. So what else you can do? So the scattering of photons on the chain of scattering centers to simulate behavior of electrons in real physical systems. There is a very well-known system exists. It's called the SSH system. It's a Schrieffer-Heeger Hamiltonian. It's when you have a polymer made of molecules, like each, like this is like molecule connected between them. And when the electron is in the molecule somewhere, it has two options: to go between atom in one molecule with probability V, or to jump to the neighbor with probability W. And when the electron propagates along this chain, because of these probabilities, there are multiple versions of energy state exist, basically. So, the most interesting thing is, I told you, so that propagation here depends on what kind of relationship between probabilities of jumps electron has. It's more like when electron going on the crystal lattice, when it gets scattered like from the corners of the lattice, and it's experiencing phase shifts basically, or probabilistic shifts. So and it goes. So if you have probabilistic phase shifts, it's equivalent of the, because original electron in the crystal lattice has a K vector associated this, the K vector, the one that from the Brillouin zone. But if you start getting shifts, it's like your vector is rotating around in the phase plane of K vectors. And when it starts rotating, there are different opportunities exist. So if the structure of this chain is such that the difference between these two probabilities is not very large, then the K vector just goes around and does not include the origin. This motion does not cover the origin. So it's equivalent to the topological transition with a winding number of 0. If the difference between those probabilities is greater, then the K vector go bigger circle in the phase space, and it will include the origin. So it will include the origin, and it will be corresponding to the topological feature with the winding number 1. And what's interesting is, as always, topological feature belongs to the whole structure. The same as like phonons, for example. They always belong to the whole thing. And because of that, they are much more stable to perturbations than the single kind of jumps of electron inside. So in principle, this can be used for the protection of particular states. So if you can encode them in such a way that they correspond to particular topological feature, it will be supported. And when you try to go away from that, it will not be allowed, because topological move out of the topological, one topological feature to another one will be prohibited by the structure of the Hamiltonian. And so you will need to have a basic topological transition that requires significantly greater energy. So to some extent, it's passive protection of features through the topological thing. So what we have, when we look at this, we use originally it just to show that with our systems, like each triangular here, one triangular here, and one triangular there, here's the written here more explicitly. You take these two triangulars that we designed, put them like this, you put the phase shift in there, and it becomes this one of the unit. You see phi A or phi B. So, and then you start sending photons like from left to right. And when you, and this is a boundary, and this is like long chains going to the left, going to the right. On the left, photons will go phi A, phi B, phi A, phi B, phi A, phi B, phi A. And the difference between those two phi's is such that it will be winding number 1. On the right side of this, for example, you can have winding number 0 by just changing those phases. Now, difference between these phases will be smaller. And then it's a very small circle the K vector puts on the phase surface, and it will be winding number 0. So, and this is the boundary between them. This is kind of like a model. What we can do with that. The interesting thing is, let's look at this combination of those phi A, phi B. I told you it's a line. Well, every line can be connected in the circle, right? So basically, and this is our input output. Well, technically you can do it through the circulator, optical circulator. Go in and you go around, you come here and you go out, for example. So when photon goes inside here, it will experience phase shift, a difference between phase shift A and B, such that for one polarization, for example, vertical, it will be winding number 1. For another polarization, horizontal, it could be winding number 0, because difference of phases is dependent on polarizations. So we can always change, make sure that when one polarization goes here, it experiences one shifts. When it's opposite polarization, it will experience different shifts. And we can select them such that the overall topological winding number of the particle going around the circle for one polarization is 0. For the second polarization, it's winding number 1. And now we have a very interesting structure. We can call it optical register. Because what is a qubit? Qubit is superposition of 0 and 1 with coefficients alpha and beta. In physics, we have to encode this 0 and 1 in some physical parameters. In optics, we usually encode them in the polarization, H and V. So if I have this optical qubit, and if I introduce this optical qubit in this chain, it will stay there protected from change in polarization. This register, optical register, will not allow the polarization to change while the photon is inside. Basically, topology protects your state. So it's a kind of cute idea of the error protected register. That's where we started with. Because winding number, it's a global parameter. It belongs to everything. And polarization is a local parameter that you can measure. You can change if you need outside. But inside, when it's there, it's really protected from the change. The other interesting thing, so that was one qubit. Then the question is, what if you have two qubits? Two qubits allow you to construct entangled state. We all know that this like HV plus minus VH, it's two types, it's psi plus and psi minus entangled states of two photons with two polarizations. Now, if we take two of these, well, it's really circles, basically. I put it here as lines, but picture them as two big circles that I discussed before. So if you take this state that you can generate these days very easily, entangled states is really kind of a technology these days. It's nothing special to consider, sorry. So you introduce it in here. One of the photons goes in the first loop, second photon goes in the second loop. And as I told you, those loops are protecting photons from flipping. Basically, we would have the two topological units that are also entangled because each one can support either horizontal or vertical, either 0 or 1. And when you introduce the state is also in entangled state. You don't know which one goes here, which one goes there, because one goes to the top, one goes to the bottom circle. So you translate polarization entanglement into the topological entanglement of those circuits, and they become very stable because topology protects from the flipping the polarization, flipping the qubit. And that's another interesting feature. You translate topology, you translate entanglement from polarization into the topological feature of linear optical system. So that's another interesting effect. But what's more interesting is, in topology, in topological systems, there is another interesting effect. It's called the edge states. If by any chance you have a boundary between two topological systems on the left and on the right, they have like different winding numbers, for example, then this edge state is extremely, extremely stable. And this it's really very, very difficult to change this thing. So in fact, if you follow the error correction protocols in quantum information and quantum computing, there are different types of corrections. Some of the correction is redundancy based. So you take your qubit and instead of one, you make like 100 of them and hoping that if one or two changes, the majority still keeps the value. But then there is a different one that is called that use topological codes to stabilize qubits. That's exactly like a photonic counterpart of what is used in quantum computing. And these boundary states are very stable. And if we put entangled states inside, these boundary states become entangled right here. So basically, you can try to do some manipulation with those entangled topological boundary states. And that's a very interesting area of research that we are developing at this moment. Well, in terms of practicality, we are experimentalists, so we would like to have this. All these ideas are great. And as always, theory goes faster than experiment. We all know that, but we would like to go towards experimental realization. As I mentioned, we executed a demonstration of one single unit using bulk optical elements. It's, as I told you, it's about like 30 by 30 centimeters unit. And it was extremely difficult to stabilize it and so on. So we do need to put them on the chip. Today, there are two different approaches to miniaturization of photonic circuits. You may know that. So basically, the first one is illustrated right here. This is laser writing of waveguides inside the material. If you take the focused laser light inside like silica, for example, or any other material, it modifies the refractive index within the spot of the laser. And then you just step by step, you move it around. And this way you draw in 3 dimensions the waveguide inside. So, but this technology is really designed to miniaturize elements that are used for quantum information with photons. Like if you have a beam splitter, what you replace is in the integrated design, it will be this couple, just 2 waveguides coupled to each other. That's a beam splitter, 2 by 2, for example. If you have some polarization modulation necessary, you can change parameters of this waveguide. In general, waveguide is supposed to be circular, but you can make it elliptical. So it also, then you have 2 refractive indices for 2 polarizations. You can have different phase shifts and so on. If you want to have a mirror on this surface, so you have to introduce Bragg grating somewhere, Bragg mirrors. So that's a way of a traditional way of executing integrated designs. So you start with the big ones, you start to make miniature versions of that using waveguides and existing knowledge of how to make mirror, beam splitter, phase shifter, whatever. And in principle, it's possible, but it's still pretty difficult to make sure that to execute systems like we have, because you have to have 3 beam splitters, 3 mirrors with phase shifters. And that's where we learned some time ago that a group of Professor Vukovic at Stanford has initiated a new approach to this type of problems. If you need a scattering unit with particular properties, well, here is not 3 by 3, it's 4 by 4, basically. And I'll talk about this probably in a minute, what you can do with that. Basically, if photon comes from the left, it can go anywhere in this system. And then how to design this system to satisfy the criteria that we want. We want to have this matrix, 3 by 3 or 4 by 4 matrix with particular elements in this. How to do that? And they designed, they used the technique, developed technique that is called the inverse design. They say, okay, we don't want to know what kind of particular elements will be inside this circuit. What we want to know boundary conditions. What is outside? What do we need to expect on every outcome of this circuit? What kind of magnitude do we need to have there? So they originally designed this for telecommunications. You put all this and then you do inverse design. You ask yourself, what kind of scattering elements inside you have to put so that on the boundaries outside, all the conditions get satisfied. That's what's called the inverse design. And they did it pretty well. They found a very strange combinations of like on the left one, you can see there are islands of semiconductor material. So this is waveguides coming in. There are some scattering elements. Basically, it's just, you can, when you calculated that, you can do lithography and make those elements yourself by etching the materials. And this is what the field simulation looks like. So this is 1 edge, 2nd edge, 3rd, 4th. And if you want to have the equal amplitudes everywhere, that's what it's very close to that. That's the results of our initial simulations based on that system. So well, in quantum mechanics, it's a little bit harder to do than in classical physics. So original design was made for the telecommunications. So telecommunications is only interested in magnitude, intensity, frequency, timing, whatever. But they don't care about phase much. So in quantum mechanics, your matrix is a matrix of complex numbers. So you have to worry about the real and imaginary part. So you need to have magnitudes and phase, which means you have 2 times more boundary conditions to satisfy, but computer can do that, can do inverse problems, and you can calculate this, and hopefully within the next several months, we should be able to have some first elements like this to try, to etch. We do using, for our purpose right now, we're using titanium oxide, titanium dioxide as the material. It's transparent, indivisible, so that's why we would like to make a system out of this element. Okay, what you can do with that, as I just want to show you the possibilities this unit opens, since we're getting closer. So you see, it's a 3-element device with 3 inputs output that serve as outputs. When this is all coherent, we can treat it as a single scattering unit with the matrix attached to it, 3 by 3 matrix. But then this type of units are very convenient to scale up, to integrate and make any kind of structures you would like to, networks. So this 3 can make this 3. Out of here, you can make elements like this. Please pay attention here. It's a combination of this one is 3, this one is 3, but this one is 4 elements right here. And also this structure already has some elements of topology visible by eye even. So there are triangulars, there are big triangular, smaller triangles, but also hexagons are available. So there could be different features for photons going inside this structure. And even further, and when you look at this picture, some of you might know what it means and have seen this before. This is the Karpinski carpet. It's a very interesting structural system for investigation. So we hope we can possibly build up an experimental model to study such type of systems. Well, then whenever you have multiple scattering units and the photons can go back and forth, you can start thinking about whether we can try to do the learning engines for the machine learning. Remember, in the machine learning, you have this intermediate layer where information goes from left to right or from right to left. But in real brain, the information always going back and forth, because in machine learning, this black dots supposed to be simulators of neurons. But neurons never fire in one direction. They always fire randomly in all directions. So we were thinking, it's a long term, of course, if we can replace those neurons with photonic scattering centers, where photons can go in all possible directions. Maybe we can try to build up something for the photonic engine for the machine learning. Because right now, machine learning is working based on computing, software. So the same as with quantum computers, maybe instead of the software, we can use physical system, optical system to do the same task. That's another interesting idea for the future. Well, then there are tons of interesting networks where the 3 by 3 units are used, or even more than that. So for example, look at this and look at this. So there are 3 by 3. And this glued tree, for example, if you move from this point to this point, it has been shown that if each scattering element here is a Grover coin, you can reach from left to right significantly faster than any classical quantum walk can do. So that's where the walk on distributed systems can benefit from the fact that scatter at each of this element is done using Grover matrix, not any other classical scattering matrix. Okay, and here there are hexagonal units. It's another interesting element. This one is 4 by 4, all elements, rectangular lattice. And on the previous slide, I wanted to show you, so there is a unit I was talking about, 3 by 3, but this unit is 4 by 4. It's also available, and I told you that it's even easier to implement experimentally using inverse design. The symmetry of 4 by 4 is easier to implement. And what we discovered recently, very interesting effect that it has also some potential benefits for networking. In the regular Horn-Gould-Mandel experiment, you take 2 photons, you send them to the beam splitter, and the probabilities of having 1 and 1 on both sides get canceled. Only you have 2 on one side or 2 on the other side. This is when you have a Hadamard coin. If you have a Grover coin, first of all, in 4 dimensions, Grover coin has a very nice symmetric representation. And this 4 by 4 unit can be treated as this is the scattering element that can implement this Grover coin, 4 by 4. 4 means that each of these elements can be input and each of them can be output. So that's why there are 4 times 4. So you can come from any in and you can go from any out. And what's interesting is we discovered that when you put the same 2 correlated photons as in Horn-Gould-Mandel effect inside through the port A and B, what happens, it got separated in the left going and right going amplitude, but without any cross term. It's only going to the left, only going to the right. It's just an effect of the symmetry of the input state, 1-1 correlated state, and the symmetry of the Grover coin. As a result, we ended up with very interesting higher dimensional Horn-Gould-Mandel, what we called. Regular Horn-Gould-Mandel is just 2 outgoing modes. Now, what we have here, we have the scattering unit, 2 beam splitters, and 4 modes, 1, 2, 3, 4. So the input is always 2 correlated photons. We put 1 in here, 1 in there, using circulators, and let them go. And you can see that if there is nothing there, just system like this, it could be 2 coming here or 2 coming there. It's like a Horn-Gould-Mandel effect, but with 2 modes that are 2 out of 4. What's more interesting, if you put a pi phase shift right here, this one, you change where the output probability can go. So now it's 2 here or 2 here. It's like 2002 state realization in these 2 modes. If you put 2 phases right here and right here, you also again change it. So you can switch where this 2002 state will show up. It's highly non-classical state. It's entangled state, 2002. And you can manipulate it in 4 spatial modes. It's like a switchboard, quantum switchboard, where you decide by checking those phases. And it's usually like some phase shift on the waveguide. It's very easy to implement. Pi phase shift on the waveguide is just few volts of electricity applied. And you can switch this between 4 different modes. So we are trying to figure out what kind of application we can build up out of this, but it's an interesting, cute consequence of the symmetry of Grover coin and 2 photon correlated states. Our next step would be to see how the entangled states are behaving in this system. That would be interesting to analyze. Okay, so basically we coming to the end. So I've discussed the new direction in unbiased 3 ports and 4 ports that open fresh opportunities. That open fresh opportunities in quantum simulation of dynamic Hamiltonians. They can practically realize some topological features connected with polarization and the structure of the network. And these topological features could help to protect the polarization from flipping from the error. So you can make a noise immune qubits. The quantum walks on graphs of different designs. It's a very interesting possibilities. We still looking for interesting applications. It's a complex thing, but also we hope to find some useful application of that. And quantum neural networks and propagation of quantum states in large networks made of Grover coins. Now it's the interesting thing we observed. You introduce 2 photons in this network, the probability amplitude split and start propagate like bullets, like solitons. So it's like at the solitons at the quantum level. So when you have this system, it should be some interesting effects and some interesting applications that we're studying right now. And of course, the most important thing is miniaturization and integration. That's what our major task right now, to put it on the chip, put many of them, and try to execute all interesting theoretical features that we predicted in practice. With that, I just would like to acknowledge support of the agencies that helped us to work on this for the last 4 years. And this is the book that we published recently that has some other interesting quantum measurement, imaging, and communication applications. If someone is interested, you can just read it. And if you have questions, I'll be happy to discuss it regarding those techniques, because of course it's impossible to cover everything just in 1 hour seminar. So, and with this, I would like to thank everyone for attention. And if you have any questions now, I'll be happy to answer.
Thank you very much for this very nice, instructive, and comprehensive talk. Questions, please. We have questions from Kadir Durak. Alexander, will you please read?
Just a second. Where is the chat? Hold on for a second. I'm trying to find the pose and update participant security. Oh, okay, here it is. Okay. Between nodes seems large even for a sub with discrete component. Reason for this? Well, the question is, the 30 centimeter distance between nodes seems large even for a setup with discrete components. Is there any reason for this? Well, the reason is just experience of the graduate student who is trying to accomplish that. Of course, we all know there are much smaller, much tighter compartments. You can basically package it a little bit more tight, but while the experience of tight packaging comes with time, and for the graduate student, that was the first time it was easier to do when they are a little bit more separated apart. And that's the only reason. There is no any other limitation. So I'm sure that right now, on the second attempt, he could do it much smaller. But there is no principal reason to do it like, instead of 30 centimeters, to do like 4 centimeters or 5 centimeters, because there is principally the same problem, stability of the whole system. That's why we go in and developing right now on-chip system that would have probably like 10 by 10 or 20 micron size altogether. And that's plus we're trying to eliminate the discrete element structure like phase shift versus the beam splitter, mirror, because even like putting the mirror, traditional mirror on the chip, you know, like Bragg grating would have significant size. So that's why we decided to go like more non-traditional way when we learn about the inverse design, to make it 4x4 scattering units in such a way that it will satisfy our matrix of amplitude and phase on the boundary conditions, and we don't care what it is inside. Yes, we cannot modify it, it's harder, but it's easier in terms of manipulation and more stable.
Other questions, please? Yeah, we have a question from Emir.
Okay. How sensitive is the system to the reflection transmission of the beam splitter? Does the system have to be balanced so that, yes, the answer, have the system to be balanced so that all the beam splitters have same transmission reflection. Yes, the answer is it all has to be 50-50. So it's all designed. However, this question opens a very nice door to another possibilities, because if you change the reflection transmission coefficients of beam splitters, you can have completely different matrices. It allows you to change the structure of the matrices. For us, for the first test, it was kind of a negative effect. If your beam splitters are not 50-50, you have to somehow balance them in order to get the result you want, the matrix. But in the future, if we want to do that, we can manipulate this reflection transmission ratio, and we can design to construct a much more complex and interesting matrices if needed for some particular processes. So that's the answer to this question. Where you can find the book? Well, it is available on Amazon, or you can try to find some PDF file somewhere on the internet. So that's where the book is available. But it's freely available on Amazon, I believe. Other questions? You're welcome. Yeah, I was just thanking for the presentation. Thank you for your attention. It's a pleasure. And I really hope we can talk more about this sometime in the future in person. I would love to come. Yeah, because
certainly we hope also.
The last time I was in Turkey was in 2002, I believe. The Alexander Shumovsky from Bilkent University organized that school. Unfortunately, he passed away some time ago.
He was my teacher indeed at university.
Oh, okay.
I knew him very well.
Yeah, he was my old friend too, from mid 80s. I met him first in 85. So he was a great guy.
Yeah, exactly. Alexander, if no other questions, maybe we can stop here. What do you think?
Yes. Yeah, I think, yeah, thank you very much. It was a real pleasure.
Thank you.
And let's keep contact, stay in touch, and in the future, hopefully we'll see each other. But if someone would like to discuss anything, just you could share. I mean, my email is on my website, and my website is very easy to find. Just type my name in Google, and it will show up. So.
Yeah, thank you.
Okay, well, thank you. And have a great night.
Let's keep in touch. Thank you very much.
Yeah, have a great night, everyone over there. We still have middle of the day here, so it's still sunny. That's very interesting. All right, good night.
Thank you. Good night. Thank you.